cough? Fear cough? Damn it. Right, so my instincts were not taking me in the right direction. But yeah, so I found it in the book. It seems interesting. I learned something from it. The total current coming into a node or junction equals the total current leaving a node or junction. Uh, Second law states that the net Ri voltage around a loop must equal the sum of the component Ri voltage drops within the loop. So this is the second law, really, more than anything else. Basically, what it's saying is that it's a balanced system, and we have to maintain the equilibrium, I guess. And the issue is you have components here that are part of multiple circuits. So you have the first circuit, or the first junction, whatever. But this measure here applies to both the first and the second, right? So it's contributing in both cases. So that's a little bit of a different aspect of things. So it's just kind of interpreting the diagram. So I have this example, and I have something kind of similar to it that might be a little bit easier, but I like this one, so we're going to go with it. So we have 30 volts. So if we're working our way around the circuit, so we're just following this path. All right. So ohms, right? Yeah. Current is amps. Yes. And ohms times amps is equal to volts. Still, don't need to know any of that to change an outlet. Probably, maybe you should have some theory associated with it, but make sure that's on. All right, so we have 1 ohm times the current, so the 1 ohm of resistance multiplied by the current in the first circuit, plus 2 ohms multiplied by the current in the first circuit, plus 3 ohms multiplied by the current in the circuit. Now, there is a subtraction component here. All right, because well, this is the sum of all the voltage drops, whatever that means. But this is also part of the second circuit, right? So you have the connection. So you have basically that measure being shared between the first and second circuits. So I have to then subtract off the overlap, basically. Right? So I'm going to subtract off that 1 ohm's contribution to I2. All right, and that'll simplify fairly nicely. But it's basically us saying, like, all right, we gain that for the, if we were collecting ohms, if that's a thing. We have this amount of resistance, this one, but then this one is also belonging to the other one, so it has to be subtracted off. Okay. So we do the same thing, working our way around the second circuit. We have 20 volts to play with, 4 in I2. So again, we're plus 4 in I2 plus the 1 in I2. But then we have to subtract off the 4 that also belongs to I3.
we have 40 volts to play with. 2 belong to I3. Another 1 in I3. Oh, sorry. Minus 1 going to I1.
Yeah, because for the middle two, you have overlap with multiple circuits. So we're losing 4 ohms, or gaining depending on what the dropping is. We're losing 4 to I3, but we're also losing 1 to I1. Right? So the kind of interactions among all of these subtractions balance everything out. All right, so where was I? 1 I3
plus 4 I3 minus 2 going to I4 and 4 going to I2. And then the last one. 10 volts. Did I miss one? Oh, I just wrote it the wrong way? Oh, let's see.
You know about this guy here? So we're doing 2 plus 1 plus 4 all in I3. Then we're losing 4 going to I2. Yeah, that's this one. And 2 going to I4.
So 3 in I4. Also 2 in I4. And another 2 in I4. But then we have to subtract off the 2 going to I3.
I mean, I say things like going to or things like that. That's not even remotely correct. Resistance is not, it doesn't, to my knowledge, work that way. So, yeah, it's not like in motion, it's just vernacular. Trying to make it seem like things are in motion. I don't know. Combine our like terms. Very colorful. So we have 6 I1 minus
1 I2 equals 30. Then 9 I2 minus 4 I3, and I'll put the negative I1 in front, is equal to 20, because we're going to have to make a matrix out of this anyway. We have 7 I3 minus 2 I4, and we have the negative 4 I2. Gives us a sum of 40. Seven I4. We have a negative 2 I3. Gives us a 10. All right. So it's a 4-variable system. So I have 6 for I1, negative 1 for I2, 0, 0. And then the resulting vector would start off with a 30. Negative 1, 9, negative 4, 0, 20, 0, negative 4, 7, negative 2, 40. 0, 0, negative 2, 7, 10. Challenge for a question like this, I think, obviously, hopefully, is the setup. So I'm not going to turn around and tell you, and you must do this by hand. You know, I think that's just too mean. Although I think it's going to take like an hour to type in the values of the matrix, one way or the other. All right, I'm just doing a quick double checkaroo here. It looks good. All right, so I think the decimals probably make more sense in this case. I put the fractions there anyway. So I1 approximately 6.4, 8.1, all right, so based on what the load is, it looks like we need fuses that at least would account for this amperage, or whatever the right word is. That's, of course, assuming I didn't screw any of that up. Look at the page number 38.